But now I'm going to the second application, which will not be so clear. And that is about projection onto a different matrix. So we project onto the matrix J 0, -1, 1, 0. And that was solid part of the GLS decomposition. And the projection results in the theorem that is called Green's theorem. And it says that double integral over the whole region of the curl of that vector field is equal to the integral over the boundary of a dot product again, but a dot product with the unit tangent vector. So this is unit tangent to the boundary in the, again, in the counterclockwise direction. Okay, so again, the claim is about equality of two numbers. You integrate that number over the whole region, and that's what we practiced, right? We practiced finding double integral over rectangle, over triangle, at least over a couple of different regions. This is integral over a curve, and again we practiced that, so everybody knows how to compute that. Now, what is the meaning of all that? Well, the meaning is quite different from that meaning. And this meaning basically refers to the behavior of that media with respect to rotation, right? So that number basically describes how much that gas, or rather that media, tends to rotate at any given point inside that region. So basically, it is related to the question I asked you once. Think about a pool of water and then take a small rotor that rotates and put it inside, make it spin, and, well, so that it spins and pushes water around it, so that water around it begins rotating. So that's what this number is measuring. Basically, it tells you what kind of rotor is sitting at every point trying to rotate the whole thing around it. But then the fundamental question about additivity says, if you have two rotors sitting next to each other and rotating, is it true that the result, the global result of that rotation, is exactly the sum of those two rotations? Is it intuitive? Is it obvious? What if I have more of them? What if I have hundreds of them? Right? Is it true that the total global rotation is going to be literally the sum of all those? Or maybe, in practice, all those rotations inside are going to cancel. Well, why are they going to cancel? Well, because for any rotor inside, I have neighbors rotating around it. Now, how do they rotate? Well, they tend to push water this way, and my rotation tends to push it opposite way. Now, assume that the strength of all the rotors is the same, right? Then these two attempts to push water one way and the opposite way are exactly the same. Don't they cancel? Well, if they do cancel, then all these rotations from the rotors around this one will cancel the rotation of this rotor. And well, if you have such cancellation, you wouldn't expect to have the sum at the end, right? And this is all it has nothing to do, whatever I'm saying, has nothing to do with reality, with physics, unless I really check it. Unless I do experiment, unless I stick in the rotors and measure something. Right? So, I mean, we can hardly talk about gravity and law of physics without throwing things and measuring things and experiencing that. So, now what we have here is a mathematical statement about a physical model that assumes additivity. All right? So if you assume additivity, then this beautiful theorem holds, and you can compute one way or the other way, the results will be the same. Whether reality actually corresponds to that assumption or not, that's physics business. Right? I have nothing to do with it. Calculus has nothing to do with it. So, whenever you have experiment and you believe additivity holds, you are free to apply calculus, all the strength of calculus. But if the additivity fails, well, sorry, you have to apply something else. Now, if you assume additivity at this point, then the theorem says basically that the circulation that you measure inside can be measured actually on the boundary as you follow this path and you project. So what is it that you do here? Well, you look at the unit tangent vector in this direction, this t vector. You look at the vector field at that point, and then again the dot product is equal to the component of the velocity onto that direction, on the tangent direction. Again, because that vector is the unit tangent vector. Right? So this dot product f dot t is equal to f dot t divided by magnitude of t, which is exactly component of f along t. So what it means is that I'm computing here the contribution of this vector to circulation along this path. Right? Basically, this is how much my vector is pushing the whole thing and tries to rotate it counterclockwise. Well, how close this is to physics, I don't know, but this is the way for you to think about it. And the claim now is that the total circulation you compute inside is equal to the total circulation you observe on the boundary. And again, the significance for physics and for engineering is that you relate something that happens inside to something that happens only on the boundary. And in most of the applications, the benefit is that you can only measure something on the boundary. Right? Well, the same thing, all these theorems hold in three-dimensional space. If you have vector field in three-dimensional space, you can integrate over three-dimensional volume, and that integral is equal to some integral over the boundary of that volume, over the surface. And that means that if you measure something on the boundary of three-dimensional solid and you don't have access inside, you cannot stick something to measure inside, well, you can still measure something that happens inside on average.